Okay, for number 72, which reads as follows. Neoprene, polychloropropene, a kind of rubber, is a polymer formed from the chlorinated butadiene CH2, CH, CH2. Write an equation showing the formation of polychloropropene from the monomer and show a portion of this monomer with 3 monomer units. Okay, so the monomer is a diene. And the way you could write this is as follows. I think I'm missing something. Yep, there's carbon right here.
Yeah. And that's what threw me off.
And I need to redraw this now. So it's okay. So there's the diene.
Why'd you draw it like that?
Just because it's just a Lewis structure. It's probably best to draw it this way.
I drew it all one line. Made more sense.
You can do that. I just force a habit. I kind of think about the 3-dimensional structure. So this is a pretty good 3D image of what it looks like. But you can do this. They're all the same thing. Okay?
Yes.
Now, I'm going to show you the page where they show you how to deal with this. Now, take a look here. So do you see this butadiene here?
Yes.
And it's going to be polymerized with styrene. Okay?
Yeah.
However, if you take a look, do you see this is a 4-carbon unit?
Yeah.
You see that this is 4 carbons, 1, 2, 3, 4?
Yeah.
1, 2, 3, 4.
Mm-hmm.
You see that this is also 4 carbons, 1, 2, 3, 4?
Yeah.
And these 4 carbon units come from that 1,3-butadiene. So there's actually 2 butadienes in here. And then there's a styrene, and you'll notice here the styrene. Do you see this CH2? There's the CH2. There's the carbon. There's the carbon. And then there is the benzene ring, which is right here. And then you'll notice we have 1, 2, 3, 4, another 1,3-butadiene.
Yeah.
So with this example, it's kind of important to be able to see the different pieces in the polymer. And in this case, it looks like we have 3 of the butadienes and 1 of the styrenes in this polymer. And you could try and make this polymer, you can see by using 3 times the amount of butadiene compared to the styrene.
Right.
Okay. Now let's change this to 2. 2, okay? And change this to 0. So what would 2 of them make? They would make this. Okay, so what is this? 2 butadienes. And if we look at the bonds here and here, that could be kind of the polymer. So how does this differ from the butadiene? Well, look at that CH2 double bond CH. Do you see that right here, but it's a single bond?
Yeah.
We're used to seeing the double bond go away, right?
Yeah. But
And take a look here. We see the double bond gone also, right?
yeah.
But in this one, you'll notice that where there was a single bond, now there's a double bond.
Yeah.
And that's the whole key. So if
Yeah.
you think about this, what is going to happen to this when you polymerize it? What happens to the double bond?
Goes away.
Okay, good. What happens to the single bond in the middle of the molecule?
Well, we just learned that it becomes a double bond.
That's right. And we learned by example. And what happens to this double bond?
It becomes a single bond.
Okay, so this is going to be the beginning of how we draw the product. And what did we always do with the ends of these guys?
Draw single bonds and then parentheses through them.
Okay, and we want an N here, right?
Yeah.
And we want an N here. And are there any other leftovers from this reaction?
No.
No.
So I got that. It just was kind of.
So I'm going to show you what happens because you're always interested in that.
Yeah, I think that would help not being.
Only this time I'm going to draw it kind of like it is drawn three-dimensionally.
Okay.
Okay, so there's one of them drawn three-dimensionally.
Yeah.
It almost looks like a cis, but it's not because that's not a double bond. Now I'm going to draw another one of these. And I'm going to draw a whole bunch of curved arrows in just a minute. Okay, so your initiator with a single electron makes a bond to that carbon. But a single electron is not enough to make a bond. So one of these electrons comes and helps make that bond.
Right.
So now our initiator is bonded to this carbon. And of course, what happens to the other electron here? Well, it goes to here. Now, you have a single electron here, so what happens? Well, one of these electrons comes over here and makes a bond along with that electron. So here, now you have a single bond because one of the bonds split apart into two electrons. And now here, you have two electrons making an additional bond, so you have another bond here, a sigma and a pi bond. And here, what happens to the other electron here? Well, it makes a bond to that carbon, which makes a bond here. And the whole thing repeats again. So we end up having this, and this bonds to this. And I'm purposefully drawing this like this so that you can see the two individual units and how they became a polymer. And we're going to get rid of this initiator. And we're just going to put a line there. And this is two units put together. So can you see if I do this and this, we actually have two of the exact same thing.
Yeah.
So that's how it happens. The double bond ends up in the middle because of the electron that's kind of forcing the issue.
Okay. Movement of electrons.
Yeah, so that's why we end up with a double bond in the middle, is so that we can propagate the movement of a single electron, essentially.
So the initiator adds a single electron and that kind of initiates this change.
And that's why it's called an initiator.
Okay.
It gets the ball rolling. And you know, when they decided that they wanted to call it an initiator, there was a struggle. Some people wanted to call it an initiator. Other people wanted to call it the thing that gets the ball rolling. And they decided on initiator because the thing that gets the ball rolling is just too long. And then someone said, well, it's not really a ball, it's an electron. And they said, well, the thing that gets the electron, no, that doesn't sound right. So they just said, you know what, how about we call it the initiator, and that's what they settled on. And then guess how it ends?
Doesn't.
It can end with another initiator, right? Because the initiator has a lone electron, and this guy goes to an initiator, and boom, it ends. But they said, you know what? It's not really initiating anything. It's kind of ending it. So let's call it the endinator. And someone said, well, there's actually a word for that. It's not endinator, it's called terminator. And so they decided to call it an initiator and a terminator.
Okay.
And that's how it worked. And then a guy read about this reaction. He was an organic chemistry student, and he thought, terminator, wow, that sounds like a great name for a movie. And history was made.
Do your kids still put up with you?
Pardon me?
Do your kids still put up with you?
No,
Okay.
I don't tell them stupid stories like this because they think everything I tell them is stupid.
Even chemistry.
Oh yeah, they hate chemistry.
Number 73.
Well, we're not done with 72B, are we?
No, we don't need to do B. It's okay.
Well, actually, we almost did. Here's 2 units, right?
Yeah.
Just add another one and it's 3.
Mhm.
Okay, so that's 72. What next?
73. When I did this problem,
Polyacrylonitrile is a polymer of acrylonitrile, which they show us here. Write an equation for the synthesis of this polymer. So they want to know so what may be kind of fooling you here is the wording.
oh no, I think, I don't know about that nitrogen. There's the carbon and the nitrogen bonded together, but that's not enough bonds for the nitrogen. So I just
This one, you just do this.
want to see how. Yeah, that's what I have. But that nitrogen only has one bond.
What do you mean it only has one bond?
Well, it's bonded one to the carbon that it's next to.
So do you remember how if we write this, it can also be written this way?
Yeah.
So this carbon is bonded to this carbon. This carbon's bonded to this oxygen. This carbon's bonded to this oxygen. That's only 3 things it's bonded to. You don't see the double bond in this condensed drawing, do you?
No. So,
See
okay.
here.
Yeah, I see.
What kind of bond do you think it is?
A double. No, triple. Because carbon, yeah, carbon and nitrogen are often triple bonded.
So whenever you see a carbon next to a nitrogen like that, you're supposed to think automatically this.
Right. So then now carbon has its 4. Okay.
These are the same thing. And that's a very common thing in organic chemistry. When you see a CN like that, you're supposed to think this.
Okay.
Okay. And that was pretty easy.
Yeah. So I think I'm okay on 74. 83A, I struggled with.
Okay, let's look at 83A. Write an equation for the following polymers: polystyrene from styrene. So this is number 83A. So this is styrene, and I'm writing it not in the form the book gives it to us, but I'm writing it in the form that will allow us to draw this easily from the monomer to the polymer. So they have C6H5, right?
Yeah.
And what that is, it's really this.
Okay, because I drew it as a chain.
And it
But
won't work because you get too many hydrogens.
yeah,
But if you count that, how many carbons do we see? 6 in the ring, right?
I guess I should have known it was benzene because styrene and benzene.
Also, well, not because of the benzene, but because of the C6H5. C6H6 is benzene.
Mm-hmm.
But if you attach it to something, you have to take one of the hydrogens off. So you're going to have C6H5.
Okay, yeah, that makes sense.
So this is going to make, but the beautiful part about this problem is you don't need to know what the C6H5 is. You can just write C6H5 in your answer.
Oh, okay.
Because it does ask for the equation. Well, let's see. Write an equation for the formation. So if I had written this, that's an equation for the formation. Whoops, I need an N.
Okay,
Even if we don't know what this is.
right. It could just be A or whatever.
Right.
Oh, okay. So I was making that harder than it needed to be.
Okay. So we good on that one?
Yeah, I just want to write it out real quick.
Sure.
The correct way.
I'm still hungry.
102.
Okay. Here's 102.
Yeah.
Nylon 6 is a polyamide formed by polymerizing this. Write an equation for this reaction. So this is still a condensation polymer.
How do you know?
Well, hang on a second. Dang, how many CH2s are there? 1, 2, 3, 4, 5. Oops, they wrote CO2H. Well, I see on this end we've got this, right?
Yeah.
And I see on this end, we've got this.
Well, that's what I had a problem with drawing. I didn't know what that meant.
CO2H.
Yeah,
Well, if we draw this part right here, we know it's this, right?
yeah,
So what's it bonded to on the left? And the answer is that carbon.
yeah.
What's it bonded to on the right?
Um,
That carbon.
yeah.
So now we have to think, how do we put an O2H on this guy? And here's what we could do. We could do this, this, and this, right? But that
No,
doesn't seem very reasonable because oxygen's not going to have the right number of bonds and so forth and so on. So we don't like that.
uh-huh.
So then we think to ourselves, well, what if it's supposed to be an oxygen like this and an OH, because we've seen something like that before. And we put a double bond there because we know oxygen likes 2 bonds and carbon likes 4, and that looks like a match made in heaven.
Um,
So that's
okay,
what that is.
that's
So
what
there are
that
many
is.
different ways of drawing this. There's this way. There's this way. There's this way. This is my least favorite. It's not even a favorite. This is my least liked one. And the reason I don't like this is because you see the O2? That makes you think that the oxygens are kind of the same, right?
Yeah,
Because you see H2, the hydrogens are the same, right? One hydrogen, both one. This makes it seem like the oxygens are the same. Are
yeah.
they the same?
No,
No. Now, why would you write 2 oxygens like this instead of writing O2? And the
kind of
answer is
differentiate.
because they're not the same. So I'm okay with this one, but
Yeah.
I like this one the best. So if I wrote this structure out, this is the way I would write it if I were to show you the condensed formula, which is what we're showing you. So there are 5 of these CH2s,
Yeah.
and then this is the carboxylic acid. So this is the way I would write the condensed formula.
Okay.
Okay.
So,
And I would actually write this.
with the 5.
That's right.
So I know now that I have it written correctly that the OH is going to come off and bond with an H to make water.
That's right.
That's all I got.
So you have this, right? And the OH is going to come off and an H is going to come off, right?
Yeah.
And so I'm going to circle this and one of these guys, and they make H2O. What is this reacting with?
What do you mean?
Well, an OH comes off, but what is it reacting with?
I don't know.
The OH, what does it react with?
Hydrogen
Okay, from where?
from the amine group.
From here, right?
Yeah.
Okay, so that means that we would have the amine group
Next.
and then CH2, COO, and then that OH would react with another amine group, right?
Yeah.
And so forth and so on. So what would the answer look like for this problem?
Oh. We would
Can
put parentheses.
you see that's the repeating unit?
Yeah.
So you would write NH, boom, CH2 5, C double bond O, boom, 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 N. Plus what?
Water.
That's right.
Hmm,
And that's how you would write the reaction.
okay.
So in this case, it's not a diamine and a diacid. It's a molecule that has both an amine and both an acid on it, and they can also polymerize. As long as you've got an acid on one end and an amine on the other. What else do you think can polymerize in addition to something that's got an acid on one end and an amine on the other?
An alcohol.
Yes. So if we had an alcohol like this, and an acid like this, it too could polymerize. And what would the reaction product look like? What would the polymer look like?
Well, we would have an ester.
Right. Go ahead and draw your product and then we'll compare answers. When I say compare answers, I mean you're going to look at mine and see if yours is the same.
I think we did a problem like this recently.
Let me know when you're done and then I'll draw the product.
Okay. Almost. Okay. I think that's it.
So I'm going to take the hydrogen off of the alcohol and the OH off of the acid.
Right.
And when I take those pieces off, I'm going to put a bond there and parentheses through those bonds and an N. And I'm also going to put H2O. That's the polymer. This is also a polyester.
Right.
That's going to be an ester bond. That's going to be an ester bond. You know?
Okay.
Now, let me ask you this. Why might you not want to use something like this to make a polymer? Now, this we saw made a polymer, right?
Yeah.
Watch this. So do you see I have 1, 2, 3, 4, 5 carbons plus my carboxylic acid? 1, 2, 3, 4, 5 plus my carboxylic acid?
Yeah.
Okay. So can I take an OH off my acid and an H off of the nitrogen and make something that looks like this? A bond there. Can that happen?
Well, haven't we done this before?
Yeah, this is called a lactam,
Lactone or, oh, TAM, because it's,
and because it's an amide.
uh-huh,
So this can happen. And that's why you might not want to make a polymer where you got one end being one thing and one end being the other, is because it could just polymerize to it, not polymerize, but form a ring.
instead of a continuous unit.
Yeah, the reason this doesn't happen too much is because the ring is too big. A 7-membered ring is not very good. See 7 atoms in the ring?
Yeah.
Not very good. But you probably aren't going to do this with 6 atoms or 5 or 4 or 5 or 4, because they make pretty stable rings.
Okay.
So if you got rid of one of these, you would end up making this. And that's a pretty stable ring, a 6-membered ring. And if you got rid of another one, you'd make a 5-membered ring, and that's a pretty stable ring.
Okay.
But with 7, you probably aren't going to have too much of a problem when you have those 5 in there, plus the nitrogen and the carbon, making 7 in your ring. These are things that are finer details that you would learn about in organic chemistry. They don't talk about in the book here.
Yeah.
So you're just getting the rest of the story from Tony.
Okay. Number 106.
Okay, hydrolysis of an unknown ester of butanoic acid, and here they have the butanoic acid, produces an alcohol A and butanoic acid. Oxidation of alcohol A forms an acid B that is the structural isomer of butanoic acid. Give the names and structures for alcohol A and acid B. Now, this is a problem you don't really need to know because we did not talk about oxidations of alcohols.
Okay.
So, do you want to learn about oxidation of alcohols, which you aren't going to need for the test, or do you want to skip it?
Well, I assume it's just adding oxygens.
Yes and no. Okay, you asked for it. So when you oxidize an alcohol, this is a methyl alcohol, and this is the symbol for oxidation. When you oxidize an alcohol, you often use something called potassium permanganate or potassium dichromate, or something, that's got a lot of oxygen in it, okay?
Okay.
In this reaction, what happens is this: a hydrogen gets yanked off of here and of here. So what I'm going to do is I'm going to take this hydrogen down here off on the bottom, and the hydrogen off of the alcohol. Okay, so this is what we have left, but it's not a very good Lewis structure. This is what happens.
Okay.
Now, it turns out that it doesn't stop here. In this case, what happens is this. You add another oxygen between this carbon and that, and you make a carboxylic acid.
Okay.
Now, let's say that you have this. So this is ethanol.
Yeah.
When you oxidize ethanol, you get the same thing that you get when you oxidize methanol, only you get that. So you have a CH3 here to the left instead of an H. But it doesn't stop here. So if we look at what happened above, we stick an oxygen between the carbon and the hydrogen, right?
Yeah.
But guess what I'm going to do right here?
Put an oxygen.
Okay. So you know how they say that when you buy old wines, you don't know if you're getting vinegar or the wine itself?
No, I don't know that.
Oh, well, clearly you don't collect wine. When you buy old wine, sometimes they open it up and it tastes like vinegar because it is vinegar. And the reason is that the alcohol has been oxidized with air to become acetic acid, which is what makes vinegar tart.
Yeah.
Okay, now let's look at another alcohol. Do you see with this alcohol, we have two CH3s attached to it?
Yeah.
So here I took off this H and that H, right? I'm going to do the same thing again. And the oxygen becomes double bonded, right? Now notice for these two, we had to stick an oxygen between the carbon and the hydrogen. Is there any carbon-hydrogen bond here?
Not there.
Nope. So that means that it doesn't go any further.
Okay.
And if you have this type of alcohol, you'll notice that we have to have an H here and an H on the carbon, right?
Yeah.
H and H, H and H, H and, oh, no H. So what's going to happen here?
Nothing.
What does NR stand for?
Not reactive.
No reaction.
No reaction. Okay.
Okay, so you can see that oxidation of alcohols is not quite as simple as we had hoped, right?
Yeah.
Okay, so now let's do this problem. So 106, you take an ester that looks like this. And you see how it says CO2R? What am I going to draw here?
C double bond O
R.
O R.
R is what we're trying to figure out.
Okay.
So when you hydrolyze this, you make an alcohol and an acid. And they tell you that you make butanoic acid. So I'm going to draw this a little bit differently. And I'm going to draw this out like that. Now, why am I drawing that bond there?
We're going to break it.
We're going to break it. And this helps us to see what we're going to get. So can you see we're going to get CH3, CH2, CH2, C double bond O, OH. And of course, this is reacting with water.
Yeah.
And usually there's a base here like sodium hydroxide.
Yeah.
And this is called hydrolysis.
Yeah.
Because you're using water to break it. Lysis means break, and hydro is for basically water. Okay, so plus we're going to get HOR.
Yeah.
That's the alcohol.
Right.
So oxidation of the alcohol. So I'm going to write this differently. I'm going to write ROH. And oxidation of the alcohol results in
Butanoic acid.
butanoic acid. So we got to take this guy and work it backwards. So I'm going to go ahead and start with it, but what would I have to make this guy?
Well, um,
Wouldn't I have to have the same thing? Except what? That oxygen shouldn't be there, right?
right.
Okay, but then how do I get the double bonded oxygen from an alcohol?
We need water.
Nope. There's my H and my OH, and that becomes a double bonded oxygen, right?
Oh yeah.
So this is the alcohol. What's another way of drawing this? So what's the name of that alcohol if you had to name it?
Um, butanol.
Close, really close.
1-butanol.
Yes. So that is the alcohol A.
Oh, okay.
Oh, wait, it says it's a structural isomer of butanoic acid. So this is not a structural isomer of butanoic acid, is it?
Alright.
So we got to start off with a structural isomer of butanoic acid. So how are we going to draw that? Well, I'm going to go back to my good old this. Here's butanoic acid. Can you draw a structural isomer of that?
Um, put it on.
Well, first of all, how
Oh,
many carbons do we have in a row here?
4.
Can we make anything else that has 4 carbons in a row?
Oh, cyclobutane.
Well, and still have it be a carboxylic acid?
I guess not.
No. So to make a structural isomer, if we've made the longest one, what do we do next?
Move it over.
Not move it over, make a shorter one.
Oh, and then add a methyl.
Yes. So here, isn't that a shorter acid?
Yeah,
Where are you going to put the methyl?
on carbon 2.
I like the way you hesitated because you were looking here and here and you thought, oh, it's on carbon 2, but then you hesitated and said, well, wait, we don't start there. We count over there, but it's still carbon 2.
Yeah.
Okay, so this is actually the alcohol, the acid that we have to make. So here's my ROH, and we have to make this acid, which I'm going to write as follows. Okay, since I've messed this up, I've run out of room, and now I'm going to rewrite this on another page. So our alcohol, when we oxidize it, we get this. And I'm going to rewrite this just a little bit differently. Okay, so here I'm going to do this a little differently again. I'm going to start over here. So when we oxidize our alcohol, we have to get this. But where does this come from?
Mm,
Comes from here.
yeah.
Okay, but that's not the alcohol. So where does this come from?
Hmm.
Well, where did the double bonded oxygen come from?
From the alcohol?
From the OH, right?
Yeah.
Now this guy still has this hydrogen here.
Yeah.
And of course it needs something else to make it complete.
Right.
Hydrogen, right?
Yeah.
Okay, so this H and this H get removed to make that. And then this has an oxygen inserted to make that.
Yeah.
This must be the alcohol that came off of the ester. What would you call the name of that? What would be the parent name of this guy?
Pentane.
What's the longest carbon chain?
Propane.
Propane. So we're not going to call it propane. We're going to call it propan
All.
all. Where is the alcohol?
On carbon 1.
Okay.
Or 1 propanol.
So 1 propanol, but if this is carbon 1 and this is carbon 2 and this is carbon 3, what is this guy?
2 methyl.
2 methyl. So if we write out the whole reaction, we have this CH3, CH2, CH2, C double bond O, O, CH, CH2, C, CH3, CH3, and I'm going to put CH there. So I can draw this a little bit better by using some white out here. And write CH3. So can you see that I have 1, 2, 3, 4 carbons that's going to become butanoic acid?
Yeah.
And I have 1, 2, 3, 4 carbons that's going to become my alcohol.
Right.
So when we add water and hydrolyze this, we get CH3, CH2, CH2, C double bond O, OH.
So there's our alcohol.
That's our carboxyl.
Acid. Yeah, acid.
And I'm going to put an H on that oxygen and CH2, CH, CH3, CH3. So this is the acid and this is the alcohol. And then they say that if you take the alcohol and oxidize it, so we're going to do this backwards just for practice. When we oxidize it, we take off that hydrogen and we take off a hydrogen where?
I think it's on the carbon 2. No. Or the methyl.
We take off this hydrogen, right?
Yeah.
And where's the other hydrogen we take off?
On carbon 2.
This
Yeah.
one?
Yeah.
Well, but if we took a hydrogen off of here, this says CH3 and that says CH3.
The second carbon, carbon 2.
Oh, but it's carbon 1 because it's where the OH is.
Oh, yeah.
Okay, so here, if we take this hydrogen, where are we going to take another hydrogen from?
That first carbon.
Correct.
Yeah.
Now, this is where it gets ugly, but I'm going to make it look pretty. So what happens to this oxygen?
Double bond.
I'm going to make that go up instead of to the left.
Okay.
This hydrogen, one of them is removed, but one stays. I'm going to put the one that stays to the left instead of to the right.
Okay.
And then everything else is exactly the same. Now, when you oxidize this, what happens?
We remove that end hydrogen.
We don't remove it. We insert something. What do we insert?
Oh, the oxygen in between the carbon hydrogen bond. That's our acid.
Yeah. And here, you see how this CH3 is going up and here I put it down?
Yeah.
Now, I put it down because these were kind of bumping into each other. So I wanted people to be able to see it very easily and see that they're not attached or anything. That's why I put it going down.
Yeah.
Fair enough?
Yeah.
So this is an alcohol, or this is a carboxylic acid, isn't it?
Yeah.
And is it a structural isomer of butanoic acid?
Yeah.
Well, if it's a structural isomer, it should have the same formula, right?
Right.
How many carbons here?
4,
How many hydrogens?
8,
How many oxygens?
2,
How many carbons?
4,
How many hydrogens?
8,
How many oxygens?
2.
Are they connected together the same way?
No.
Justify that they're not connected together the same way.
The
Think about naming them.
right. So we had, was it 2-methyl-1 butanol?
When you name them, what's the first thing you look for other than the functional group?
The functional group, the branches, the substituents. Well, the parent. The parent. Yeah, that's a given. So we have butanol.
Okay, so justify
Butanoic.
that these are different. What's the parent here?
It's butane.
What's the parent here?
Butane.
Really? One,
Oh,
two,
yeah.
three.
We just did this too. It's
Yes, we did.
propane.
So
It's
you can
on.
simply justify that they are different because they have different parent chains. One's
Yeah.
a butane based, one's a propane based. That's enough to say they are different.
Yeah.
So,
Right.
Trying to get you to wrap your mind around it that, hey, when you name it, you're actually saying that they're different. And they're different because they have different parents. Or, they're different because they have the same parents, but they have different substituent placement.
Yeah.
Like a 1-2 is not the same as a 2-3. Right?
Correct.
So ultimately, they're different because either 1, they have different parents, or 2, the substituents are in different places.
Yeah.
Okay? A lot of subtleties here, huh?
Yeah.
Only I'm trying to not be so subtle about how you figure out what's subtle.
Yeah.
All right, I can see I'm boring you to death, so maybe we should call it.
I don't have any other specific questions. I don't think.
Fantastic. We've been at it for almost an hour, so this is a good time to stop. We're at it for over an hour this morning. I'm sure you're tired of me. That's why you're yawning.
Okay.
Time to pop open that stroller behind you and sit down in it and take a nap.
I know. I should. take a
You know,
nap.
if you kind of leave the computer on playing some YouTube thing, everyone's going to think you're still working. You can take a little nap.
That's funny. Oh man. Okay. Thanks for the idea.
All right, you're welcome.
Bye.
Did you say you're not going to be able to call in tomorrow or Friday?
No,
Okay,
unfortunately.
maybe we'll see you next Monday. The last day for calling in is going to be Wednesday. I'm not going to do any Zoom sessions on the final day, which is Thursday.
What?
You heard me.
Okay. I'll try to come to 6 p.m. tomorrow and Friday if I can. Oh,
Why?
not Friday. Not Friday. Huh?
Why? Just because I'm not Zooming on next Thursday?
Oh no, because I'm working and I have to do this.
All right. Maybe tomorrow, maybe we won't.
Okay, bye.